All right. Good morning, folks. Let me go ahead and start my stopwatch here as I stay under time. So this is going to be the first time we're going to be working online here over video. So uh, I'm sorry, outside of the Wednesday video. So remember, we're going to be starting the new format today. And so please make sure then that if you have questions about this video that you watched today, that tomorrow on Friday, stick around after I take roll and ask questions about it. Okay, so hopefully some of you stayed around after I took roll today to get some of your questions answered about yesterday's video. But this is how we'll be doing it. Okay, so you hopefully you'll get a chance to watch the video, or you would watch the video, and then the following day, if you have any questions, you stick around after I take roll, and then you ask your questions, and then you can go ahead and leave and then watch the video for the day. Okay, so if you did leave early and you're watching the video now, please make sure again you take advantage of the opportunities now that you have to talk to me during our class period. Since you don't have to sit and listen to the lecture live anymore, you're going to be watching this recorded video. Stick around after I take roll, like I said, and get your questions answered, and then we can do homework problems. We can do what we need to get you to understand this material. Okay. So please make sure you take advantage of this opportunity. I think it's going to help us. This format will work. It'll give you more of an opportunity to get your questions answered, okay, and be more interactive. We can engage more in discussions about what you need to know. Okay. All right. So let's keep going with this. And let me go ahead and let me start out then, and let me share with you my the notes for today, the my lecture notes. What I'd like to do to start out with then is I would like you to let's take a look at number one here in here. Let's start out with number one here. Let me I'm sorry, go ahead and do this. Yeah. Yep. Let's start out with the very first problem here in your problem set. What I'd like you to do is on a separate sheet of paper, sorry about the separate sheet of paper on, and hopefully make sure you remember then, you want to make sure you want to continue to record your submit your work. Don't forget to submit your work, you guys. Okay? So go ahead and make sure that you submit your work afterwards and get it online, get it on Classroom, and that way then you will get credit for watching the video. So you'll have till 11:59 tonight to watch the video. But again, I warned you, please don't do that. Okay, don't wait till the end to watch it. As soon as hopefully you're watching it right now, right after we dismissed you from class, that you're using the class time, watch this video. But like I said, the reason why I chose to do it this way is that it allows for a little bit more flexibility for you to watch this lecture when you can. Okay. All right. So with that said, let me ask you to do this on your paper. Let's take a look at number one here. This is number one from your problem set. So we're going to do number one from your problem set. We're not going to do all the problems from the problem set here, especially the first, the next few problems. We're not going to do this. They're basically review from first semester. So what I'd like you to do here is the questions asking you about how many p orbitals are filled for each of these atoms here. Okay, so I would like you to go ahead on your paper, write out the answer. And then what I would like you to include in here then is I would like you just to give us a chance to practice this. What I'd like you to do then is I want you to include the Lewis dot structure. Okay, so for each one of these here, I would like you to also include the Lewis dot structure for each of these atoms. So go ahead and first of all, indicate then the number of filled p orbitals for each of these atoms. And then from that, write the correct Lewis dot structure for each of these four atoms here. Okay, so we're going to use this to review. So let's go ahead and take about 3 minutes. I don't think it should take you any more than that. 3 minutes to work through number one here on your problem set. And so please make sure you also that you record this answer on your problem set so that when we take the exam for chapter 7 here, you'll submit this work. Okay, so go ahead, get started with number one from your problem set. And I'll see you back here in about 3 minutes. Okay, get started with it. Okay, let's go ahead then and let's take a look at what we have here. Okay, so if you take a look at this, and what I'm going to do here is probably going to be more than what I think you may have done, but they're asking us to identify here the number of p orbitals that are filled. Remember, p orbitals then, with the p orbitals, we have three. Remember, with the p orbitals, then there are three locations for electrons to occupy. Okay, and so in order to fill the p, so these are the two. These are the p orbitals. See, all p orbitals, regardless of what energy level they're in, all p orbitals then have these three shapes, the three locations where we can find electrons. Okay? All right, and so for these orbitals to be filled, then for these orbitals to be filled, there has to be then a total of 6 electrons to fill in to fill in these p orbitals. So you have to have a total number of 6 electrons to have those p orbitals filled. Okay, and we see then, like with the noble gases, for example, we left off with that yesterday. With the noble gases, the p orbitals, the outermost p orbitals, they are completely filled, and so are the s orbitals. And so we see that, and I'm going to pick up with that. Hopefully, I'm going to pick up with that in just a moment. Okay? All right, so with that said, then what you'll need to do with each one of these then is, if you don't remember them off the top of your head, what you should probably do is write out the electron configuration. Now, you don't have to write out the complete electron configuration, okay? But you do want to make sure you write out I'm sorry, you would write out the electron configurations for each one of these here, indicate then how many filled p orbitals are. So with carbon then, we have 1s2, 2s2, and then we have 2p2. Okay? All right, so these are the orbitals we're looking at right here. We want to examine, and we want to take a look at the p orbitals right here. So with the carbon, then you only have two electrons in the p orbital. Okay, you only have 2 electrons in the p orbital. Okay, and so if we were to write those out, okay, let's go ahead, and I'm only going to do this again for the. I'm not suggesting you do this, but I'm going to write this out here for you. So there are the 2p orbitals. Okay, so these are the 2p orbitals here. There's only 2 electrons, you guys. There's only 2 electrons, so which means then, according to Hund's rule, those electrons are going to spread out. Now they could occupy either the first square and the third square, second square and the third square, first and the third. Doesn't matter which electrons, which orbital is occupied here, but they do spread out. And so because they do spread out, we have 2 half-filled. We have 2 half-filled electrons, orbitals, p orbitals. And so therefore, how many filled p orbitals are there? I'm sorry, let me go do this. How many filled p orbitals are there? 0. There are no filled p orbitals. Okay, so no 0 filled p orbitals. Not for carbon, at least. Okay? So you have electrons in the p orbitals, but in order to fill them, we'd have to have two electrons each. Okay? All right, so that's it for carbon. Let's go ahead and let's take a look at, we'll get to the Lewis dot structures in just a moment. Okay, let's take a look at then with phosphorus. Okay? Phosphorus then is going to be 1s2, 2s2, 2p6, 3s2, 3p3. Okay. All right. So let's go ahead and let's take a look at this here. We have these p orbitals here. So we have these p orbitals here in the second energy level, and we have these p orbitals here in the third energy level. Let's go ahead and draw each one of those. Okay. So we have the p orbitals here. 1, 2, 3. Those represent then the 2p. Okay? And then we have these here, which will represent the 3p. So again, we have 1, 2, oh, sorry, 3. Okay. All right. So let's go ahead and let's take a look at it here. So with the, I'm sorry, these are the 3p orbitals. Okay? So what we have here then is we have, with the 2p orbitals, we have 6 total electrons. So we have then 1, 2, 3, 4, 5, 6. Okay, so there you have then this set of p orbitals are completely filled. Okay, all right, and with the 3p orbitals here, we have then 1. They're spread out. 2, 3. These are half filled. Okay, so how many filled p orbitals are there? We have then 1 filled p orbital right here. In the 2p energy level, we have 1 filled p orbital. Okay, so we have 1 filled p orbital. And the other set of p orbitals, okay, are half filled. So we have one filled p orbital right here. Okay, and so it's completely filled here. Okay, this set of p orbitals are completely filled. This set of p orbitals are half filled. Okay, all right. Let's go ahead and let's take a look at oxygen. Okay, let's take a look at oxygen right after electron configuration for oxygen. We have one s2, two s2, 2p4. Now, I guess, let me go back and I've had this, I just thought about this. I've had this question asked me before. Technically, you'd have one p orbital here, but the way that you can also interpret this question then is that how many of these separate orbitals here are filled? And then you would argue then there would be three, which would be fine. So I'm going to put this parenthetically then, okay? That if you interpreted this question in terms of how many of each one of these orbitals are filled, okay, then you could argue then that there are three filled p orbitals. Again, I bring that up because I just remembered then that there was in the past students who interpreted it in that manner. Okay, all right. So with that said, let's take a look at with oxygen here. Okay, so these are the this is the p orbital that we're looking at right here. Okay, we're going to be examining this p orbital right here, and let's go ahead and take a look at it. Okay, so we have then 1, 2, 3. Okay, all right. So in this particular situation, then we have that 4 electrons. You have 1, 2, 3, and 4. Okay, so we have one pair that occupies one of the spaces in the p orbitals. All right. So with that said, then we can say that again, if we're following along with what we're saying here, that there that if we're looking at the p orbital in terms of all three of those spaces, then we can say then that there are zero filled. I'm sorry, that's wrong. Zero filled. Okay. Zero filled p orbitals because you only have this one right here. Okay. Or again, if you're counting or if you're interpreting the question as asking you how many of the three p orbitals here, three spaces are filled, you can say one, then you can say that there's one filled p orbital. Either one, again, I think if I were to ask this question on the exam, I would be more specific about how you would count this. Okay. All right. So with that said, let's take a look then at oxygen, and let's finish up here. So oxygen then is going to be 1s2, 2s2, 2p3. Okay. And so with that said, then let's take a look at. We will be taking a look at these electrons right here. Okay. And so let's go ahead and let's draw out our p orbital. Whoops, sorry, p orbital. Squares since we stayed with it. Okay, so we have our three p orbitals here. All right, and we have three electrons to account for. Hund's rule tells us then that the electrons are going to spread out in such in this manner here. Okay, and so therefore then we will have 0 again filled p orbitals. Okay. All right, so this represents a 2p, this also represents a 2p. Okay, so that would be how we would approach answering this question. So essentially the answers to this question, again, I told you didn't need to do all of this. The answers to the questions then are going to be the ones that I will box in green. The rest of it, drawing these boxes, really you don't have to do that unless you need to see it. Okay, but if you don't see how we got these answers in, I would highly suggest that you draw these boxes and do what I did here. Okay. All right. I also asked you then to write down or to share with me the Lewis dot structure for each one of these here, okay, as practice. And so let's go ahead and do that as well. Okay, so to write the Lewis dot structure, remember there's two parts. You need the symbol for the atom itself, and then you need to indicate then with dots the number of valence electrons. And now we're dealing with valence electrons. Okay? All right. So to do carbon first, then carbon is the letter C. Okay. And so with the dots, and so there's the first part of the Lewis dot structure. Okay, now we have to indicate then the number of valence electrons. Now, what we did here is we just examined the p orbital. What we're doing with the Lewis dot structure then, so we have to make sure that we look at all the electrons, okay, in the in the highest energy level, which represents which is the second energy level here. So we have then four total electrons. And so hopefully you remember then that the s orbitals, there's only one space. So therefore, these two electrons fill that up completely. So we have one completely filled s orbital and a partially filled p orbital. Okay? So therefore, we have then these two electrons that are paired and these two that are unpaired. And so what we have to do then with the dot then is that for the electrons that are paired, we got to pair them up, and the ones that are unpaired, we have to separate them. So that would be the Lewis dot structure for carbon. You have one pair, okay, and two unpaired electrons. Okay. All right, let's do the same thing for phosphorus. Phosphorus then is going to be the letter. We're going to use the letter P. Okay, that's the symbol for phosphorus. So we're going to go ahead and write that down. Okay, so we're going to start out with phosphorus. Okay, and in just like what we did with carbon, we're going to examine the valence electrons, and these are the valence electrons right there. Those are the electrons in the outermost energy level. These two electrons are paired up, fills up the p orbital. These, as we've shown here, are spread out. So we have three unpaired. So therefore, we're going to have two electrons that are paired. That's these two right here, and three that are unpaired. And that's the Lewis dot structure for phosphorus. That's going to be important again. The reason why we need to draw these Lewis dot structures is because we want to be able to indicate then which electrons are actually bonding, which electrons are leaving, and which ones and the ones that are being picked up, where they end up at. Okay. All right. So with that said, let's take a look at oxygen. The symbol for oxygen is going to be O. Okay. And so what we're going to do is we're going to examine then these 6 electrons right there. Those are the valence electrons for oxygen. Again, what we need to notice here is that we got 2 pairs here. We got a pair here. These 2 are paired up, and by drawing this header, we see that there's a pair right here as well. So we have 2 electron pairs. Okay, so 4 of these 6 valence electrons are paired, and then 2 are not paired. So to write them out that way. Okay. All right. Finally, with nitrogen, then we're going to write down the symbol for nitrogen, which is going to be N, and then we're going to look at these 5 electrons right here. Okay, there are the 5 electrons. Okay. And if you notice again, we have a pair here, and these 3 here are spread out. They are unpaired. Okay. And so we write this out then with 1 pair and 3 unpaired electrons. So the dots then represents the valence electrons. So that's what we have right there. Okay. All right. Very good. So check your work, you guys. Check your work and see if you get this here. Okay. If not, then that's fine. Hopefully you'll write this down in your problem set and use this to help you study for the exam for this chapter. Okay. All right. I'm gonna go ahead and save this, and I'll post it for us. Well, let's continue on. And let's take a look at where we left off with yesterday. Okay. So I explained to you then that the stability of noble gases are a result then of each noble gas having eight valence electrons out in their outermost energy level. Okay. They have a total of 8 electrons. Why? Because the s orbitals are completely filled and the p orbitals are completely filled. It's the filled nature, and this is what I would like you to make sure you understand. Because when we start talking about pseudo noble gas configurations, we're going to achieve something like that. But if you notice here, then we have completely filled. The s orbital is completely filled, and the p orbitals are completely filled. Okay, and make sure you remember this is the reason why I wanted to start out today with the discussion of orbitals here. Okay, because you need to recognize that. Okay, so the s orbital here has one space. The p orbital here has 3. Okay, and we know that they're completely filled because if you look at it in here, okay, 2 electrons in the s orbital fills that up. According to the Pauli exclusion principle, remember a maximum of 2 electrons will fill in that space. Okay. For the p orbitals, then we have 6. So therefore, okay, the p orbital is going to be completely filled. Okay. So for any noble gas, you're going to see this right here. And again, this is going to be true for the valence electrons, but this is going to be true for any s orbital, any p orbital for the noble gases. Okay. For the noble gases, they have all their orbitals completely filled. Okay, so because of this completely filled. Oh, yeah, I got to work on that spelling. Sorry. So completely filled orbitals equal stability. The atom will be stable. This holds true for the most part, you guys. And this is going to be true for when we talk about the pseudo-noble gas configuration as well. So completely filled orbitals. When we talk about the transition metals and the intertransition metals, okay, we're going to talk about d orbitals. Okay, here we're focusing on the s and the p orbitals. Okay, but make sure you keep that in mind. This is an important concept here that we will come back to as we continue our discussion of why and how ions form. Okay, so completely filled orbitals, not completely orbitals, completely filled orbitals impart stability. There's stability to be found in a completely filled completely filled orbitals. Okay? All right. And so therefore then, if for noble gases, if the s orbital is completely filled and 8 and 6 and p orbital is completely filled, you notice then here the total number of electrons that we have here are 8. Okay, and so that's where this rule then that we call the octet rule comes into play. The octet rule just simply says then that if an atom can achieve then an octet, okay, then it's in its outermost energy level. If an atom, any atom, can achieve an octet in its s and its p orbital, it will become stable. So let me repeat that. If an atom can achieve a completely filled s or a completely filled p orbital, it becomes stable. How it does that will vary from atom to atom, but that's the idea. Okay, and so that's why with the octet rule, what we're saying then is that when an atom forms a compound, when it changes, okay, what it's going to try to do then is it's going to try to achieve an electron configuration that resembles that of a noble gas. Okay, so that's what the octet rule is essentially saying then. And that's what we want to make sure you keep in mind, that the electron configuration is that of a noble gas, not that it becomes a noble gas. And that's where in the past students have had some of their issues. They somehow in their mind, they think that, oh, if an atom achieves an electron configuration of a noble gas, it becomes that noble gas. No, remember the identity of an atom is determined by the number of protons. The chemical and physical properties of the atoms are determined by the electrons. So therefore then, if an atom can obtain the electron configuration of a noble gas, then it will acquire the stability of the noble gas as well. It does not become the noble gas. Okay. All right. So you want to make sure you keep that in mind as we move forward with this, because I will also be referring to them how a particular atom will become like this particular noble gas. And I say that, and I'm referencing the electron configuration, not the number of protons. Okay, I'm referencing the electron configuration. Okay. All right, so with that said, let's go ahead then and let's take a look at then how what the atoms do in order to become more stable. Okay, let's go ahead and take a look at other atoms that are not noble gases. What do they do? Okay. Well, first of all, what we're gonna let's focus in on the metal atoms first. Okay. Now remember, the metals are the largest group of elements. Okay, they are the largest number of elements. They occupy kind of the middle and the left-hand side of the periodic table. What metals tend to do is, in order to obtain an electron configuration like that of a noble gas, they will lose electrons. Okay? So metals will tend to lose electrons, and if they lose electrons, make sure you keep this in mind. We talked about this, and the PhET lab tomorrow. And so tomorrow, Friday, we'll be doing the PhET lab. And so what metal atoms do is that they will lose electrons in order to become a cation. Okay, so in order to obtain a positive charge, atoms don't pick up protons. Protons are not exchanged between atoms. The positive charges are not exchanged between atoms. There are no free-floating protons. Okay, it's the electron. So in order for then a metal atom to become more stable, they will lose electrons. So you got to make sure you remember that. Metal atoms always lose electrons, regardless of whether we're talking about representative metals or transition metals or intertransition metals. Metals lose electrons. They don't gain protons. Okay? They lose electrons, and because of that, then they get a positive charge. Okay? Right. So let's take a look at how this happens. Okay, let me go ahead and I'm going to open up a whiteboard here. I'm going to open up a whiteboard, and let's take a look at how this happens. Okay? All right, so let's take a look at sodium, okay, as an example here. Let's take a look at sodium. Sodium has this electron configuration here. Let's go ahead and write out the electron configuration of sodium. It's going to be 1s2, and I'm going to write all of them here. 1s2, 2s2, 2p6, 3s1. Now, people look at this and you're going to see then, and I want to highlight here, if you notice here, there, sodium actually has a filled S and a filled P. And that's why I want to write this all out for you. Okay, so you see then that sodium already has that. However, there's this one electron right out here that is also included in sodium that makes it not quite stable yet. Okay? So if somehow, so again, I want to draw everyone's attention to this fact here, that sodium already has a filled S and a filled P. That would make it stable. That would make it stable. And sodium, remember, sodium then is going to resemble neon. So if somehow sodium can get rid of this electron here, whatever's left over then is going to resemble that of neon. And that's why we write out the electron. Remember the noble gas configuration then, neon here is the noble gas. And then this is the key, this is the one difference between sodium and neon. So the point here that I'm trying to make then is that sodium can obtain an octet. That means sodium can get a filled S and a filled P, but what it has to do is somehow it has to lose this electron. It has to give up that electron right there. It has to give up that electron. Now, how would it do that? How would it do that? Well, we talked about ionization energy. We talked about how if we zap this particular electron here, with a certain amount of energy, okay, then that electron will leave. That does happen if sodium here is in the gaseous state. We're going to see then when sodium forms its ion, what actually happens here then is instead of using energy to remove this electron, a compound will form. And what that means then is that what sodium does here is that it won't absorb any energy. It's just going to find another atom that is willing to take that electron, and it gives it away. But we'll get to that. We'll get to that discussion when we talk about compounds. Okay. But the idea then is if sodium can somehow lose this electron right here, if it can lose that electron, what will be left over then is going to be 1s2, 2s2, 2p6. Okay. So what's left over here will resemble that of neon. That is neon. Now understand, this atom here that I'm going to fill in right here is not neon. It has the electron configuration of neon. Okay, so therefore, if we write down the composition, if we describe the composition of this atom here, we'll see then that this sodium here has 11 protons, okay, and 11 electrons. Okay, that's what makes this atom here neutral. Okay, what we have over here now is we have 10 electrons. Okay, if it is still sodium, which it is. Okay, if it is still sodium, which it is, and I'm gonna write it there, it should still have 11 protons. Again, the atom doesn't change its identity. Okay, remember what the subatomic particle that determines the identity of the atom is the proton. So if you notice here, the number of protons still stay the same. Okay, we have then 11 protons that we start out with here, which identifies sodium. We still end up with 11 protons. The difference now then is in the number of electrons. We have one less electron, and so therefore this atom here now has a +1 charge. So therefore, this atom here is still sodium, but it's not neutral sodium. It's not like this atom. It is a sodium atom with a charge on it. It's a positive charge, so we call that the sodium cation. Okay, this is neutral sodium here. So this is neutral sodium, or what we refer to as elemental sodium. Elemental sodium. Okay. Okay. The name of this atom then is the sodium cation. Okay. We need a different name because it is a different atom. Okay. So this is elemental sodium. It has a neutral charge. It has its full complement of protons. It has its full complement of electrons. Okay. The sodium cation here has its full complement of protons, but it is missing one electron, which makes it very different from this sodium atom here. In terms of its chemistry, it's very different. Okay. Sodium atom here is very reactive. It's very reactive. That means it wants to change. this sodium cation here is very stable. It's very stable. How do we know? This is the form of sodium that we consume. This form of sodium, which is sodium cation, is 1/2 of sodium chloride. Okay? Sodium chloride is an ionic compound. We can consume sodium chloride and nothing happens to us. Well, I mean, okay, let me take that back. If you, in our society here, we consume way too much sodium chloride, which leads to health issues like high blood pressure and so forth. But we can consume sodium chloride and nothing will happen to us. We consume elemental sodium. Let me just give you an idea. Elemental sodium, and I wish we were in class. I'll try to show you a picture of it, share with a video of it tomorrow. Okay? But sodium, elemental sodium, when you put it into water, you get this huge reaction, generating a whole lot of heat, a whole lot of light, and that's because elemental sodium is very reactive. You can only imagine if you try to consume sodium, elemental sodium, that would not be a good thing. Okay? And so therefore, that's why these atoms are very different. We need to give them different names because their compositions are different. Their chemistry is different. They are different atoms. Even though they are both sodiums, they are different sodium atoms. Okay, so you want to make sure you keep that in mind. And so we notice then that the sodium cation then now has an electron configuration that resembles that of neon, and that is why sodium cation is stable. And so if you notice here, the sodium cation has its full complement now of electrons. There it is. There's our 8 electrons, and so there is our octet. Okay, now sodium has achieved its octet. Not by gaining any electrons, but it now has achieved its octet in the highest energy level here because it loses that 1 electron. It loses that 1 electron. Okay. All right. Let's go ahead then. Let's take a look at another example. Okay. So let's take a look at another example of an atom, of a metal atom, okay, and what it does. Okay. All right. So with that said, then we have calcium. Let's take a look at calcium. Calcium then has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, so there it is. Now we have an alkaline earth metal. Okay, all right. Same thing here. If you notice here, let's take a look at what we have here. We have a filled. Oops, sorry. We have filled S and a filled P right here. Now, I mean, you could see that it has a filled S and a filled P right here in the second energy level, but we also have a filled S, a completely filled S orbital and a completely filled P orbital right here. So therefore, then if you take a look at this right here, that resembles argon. Okay, that noble gas then is going to be argon. So again, if we were to write this as a noble gas configuration, we'd use argon. Okay, so how then could what could calcium do in order to obtain the electron configuration of argon? What could calcium do to get that done? Okay. Now, if you notice here, sodium would only needed to lose 1. Sodium only needed to lose 1 electron in order to achieve the electron configuration for neon. If you take a look at calcium, calcium has 2 electrons here. So one would argue that, wait a second, calcium has a filled s orbital. Isn't that already half of the equation? And I would say then you were right. Okay? However, the octet rule, the stability of noble gases is not just the filled s orbital, it's both the filled s orbital and the filled p orbital. Both have to happen. Okay? You have to have a filled s and you also have to have a filled p. And so therefore, calcium is not stable. Calcium actually is a little bit more stable than sodium. Calcium is a little bit more stable than sodium, but that doesn't mean that it's stable. What calcium has to do then is it has to try to shed and lose both of those electrons. Here, with sodium, all it had to do was lose 1 electron. Okay, it has to lose 1 electron and it's stable. Here, for calcium, in order for it to obtain the electron configuration for argon, it has to lose 2 electrons. It has to shed both of those electrons. Okay? Because if it's able to do that, if it does shed those 2 electrons, what's left over? It has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, which makes its electron configuration like that of argon. So therefore, whatever atom of calcium that we have here will be stable. Okay, it will be stable because if you take a look at this here, there it is. It has an octet here. Now, sure, it also has an octet here, but we're looking at the outermost energy level. Okay, so it has achieved its octet. By losing 2 electrons, it has achieved its octet. Losing only 1 electron will not allow calcium to obtain this electron configuration. It has to lose 2. Okay, it has to lose 2. And so if it loses 2, okay, let's go ahead and take a look at this. Okay, remember, this represents the neutral atom. Okay, and so we refer to this then as elemental calcium. Okay, so that's the name, calcium. Okay, that's the name of this atom right here. The name of this atom here is elemental calcium. Okay, calcium, sorry. So that's elemental calcium, and the elemental calcium then has a 22, yeah, 22 protons. Let me just make sure, 10, I'm sorry, 20. 20 electrons, 20 protons, sorry. Okay, you got 10, 20, okay, 20. And then therefore it has also 20 electrons. Okay. All right. The composition of this atom, whatever it is going to be a calcium atom. It still has to be calcium because it will still have its 20 protons. Okay. However, now we only have 18 electrons. Okay. And so if the elemental calcium is neutral, whatever this atom is, it's going to have a 2+ charge. Okay. And so therefore, this atom here is still calcium, so we'll use that symbol still, but to make sure that we indicate that it is a different calcium atom, we're going to indicate the charge here. The charge that is left over here, just like we did up here, we indicated the charge here. Okay, we're going to do the same thing here. Why? Because this calcium atom is not neutral, it's not elemental calcium. This is the calcium cation. It is a different atom of calcium. So we give it a different name, and we have to make sure we give it a different symbol as well. Okay. All right. So what we'll do tomorrow, and I'm so running out of time here. So what we're going to do is tomorrow I'll have a PhET lab for you to do. This will be our first lab that we will do. You'll work on it during class time. Okay. So no video for tomorrow. You'll be working on the PhET lab. And then on Monday's video, we're going to pick up with this discussion here, and we're going to talk about how then how we can represent this. This is what we call the ionization reaction. So we'll show how we represent this, and we'll practice this a little bit more with other other metal atoms as well. And then we're going to talk about then the transition metals. So sodium and calcium are representative metals. Okay, so it's pretty straightforward how these ionize. But then and then we'll turn our attention to the transition metals, and we'll see how they ionize because they're a little bit different. Okay. All right. Very good, folks. Please make sure then, if you have any questions about this, please come by and ask. Stick around tomorrow on Friday. Stick around on tomorrow after I take roll and ask your questions. Okay. All right. I'll see you folks. Have a good rest of your day. Okay.